Hi ladies and gentlemen, welcome to our first lesson in Math 344. What I'm going to do is provide you with the structure and also cover section 1.1 on how we're going to do the videos and kind of prepare for each lesson before we end up in the classroom together. So let's jump right in. We'll take a look at Strang's text here. We're going to start in chapter 1. He generally provides a single page overview for each chapter, and you can see obviously he provides the sections and the section titles. What I want to start with is just looking at a little bit of notation. It's important to keep the notation straight. Also remember, I always recommend that you watch my videos at 1.5x. 2x is generally too fast. You're going to need to pause and take notes and look through, like I said, read through the book and look through the examples. But doing them at a speed 1.0 is a little slow, I think. So we're going to start by looking at notation for vectors. Professor Strang, who with all respect I will refer to as Strang in most cases, Strang represents vectors using boldface. I don't have access to boldface, so you'll see me using an arrow. And when it comes to written materials, you'll see boldface and arrow combine. So what we're talking about in general are vectors, and vectors contain components. So for example, in general, a vector v might have 3 components, and those components are, for most of what we're talking about, real numbers. And almost every country in the world uses column vectors as the default. There are a few countries that use row vectors, but we are not one of them. So in the United States, we do everything by default using column vectors, and that's what we'll do. You'll also see sometimes using letters such as ABC to represent the components within a vector, no problem. One note for the notation that Strang uses. It's different than the notation I use. I don't like the one he uses, and I will use one that I hope is a little more consistent for you. So when Strang writes a vector in row form, he's going to use the parentheses. And I prefer to reserve parentheses primarily for points in space. And I think that writing the row vectors this way is a little bit confusing. I just need you to know that this is what Strang does as you're reading through his text. What I will do is I will continue to use the square brackets. So you will see me writing vectors that are row vectors using square brackets. I'm just being consistent with the MATLAB notation. There are other notations. Perhaps you've seen them. A very common one is to use the greater than and less than symbols for the edges of the vector. We won't use that notation, but that's one of the notations that you'll likely see. So a little bit about the way Strang has done his book. He has selected a learning method called spiraling, and what he does is he just throws us straight into the material and relies on our ability to just try, to work, to read, to think, and to continue to kind of process information. I'll explain spiraling in a minute, but let me give you an example. So he throws out, for example, the term linear combination. He doesn't give us a strict definition for what linear combination is. He just starts using it. And that's very much consistent with the way he does things. He talks about independent and he talks about dependent. He's not providing us a formal definition of those things right off the bat. He's just using the correct vocabulary to help us become familiar with this new topic of linear algebra. So what we have is we have an emphasis on vocabulary and we have this emphasis on concepts. Sorry, I've got the lines drawing here. All right, so straighten that out. And this is the approach that he is taking. The spiraling approach is an approach where we are stretching ourselves and reaching forward. And we're using this vocabulary, we're using the ideas, and we're talking about these things that we haven't fully explained. And then we're going to reach back and we're going to review things that we've talked about previously. Let me turn this feature off. That's the automatic shapes feature in OneNote. So we're reaching forward, we're stretching ourselves, we're using the appropriate vocabulary, but then we're coming back and we're reviewing. And this process continues, right? We'll review some material, then we'll reach forward. So we'll continually go over the material and we'll continue to expand on it as we move forward. This process of spiraling is one of the best ways to learn. It's something that requires us to continue to kind of march forward, even though we don't understand everything. And that's the big thing I need you to accept. You're not going to read through a section of Strang and just automatically understand everything right off the bat. That's not the way it's set up. It's set up so that it is an introduction to the ideas and to the vocabulary, and then we will continue to revisit and build our understanding and intuition associated with these things. That's the way the course is set up. So in section 1.1 here, this is one thing that Strang's includes throughout his text. Each section has an overview of the things we're going to talk about, which is great. This is the standard way of doing any presentation, where we tell people what we're going to tell them, and then we provide them with details. And we will spend time looking at these things. So he talks about linear combination. He gives us an example. And a linear combination is really built up of two things. We have scalar multiplication, where we take these things called vectors, which we'll expand on in just a minute, but we take these things called vectors and we multiply them by scalars. And then the second operation is vector addition. We just grab two vectors and add them together. And that's what linear combinations are. We take each of the vectors and we multiply by a scalar. Maybe that scalar is 1, maybe it's 0, maybe it's something else. We're sticking to real numbers. And then we take those resulting vectors after scalar multiplication, we sum them together. That's vector addition. And of course, subtraction is included with addition. Subtraction is just addition with a negative scalar that we've multiplied. So these are really the fundamental pieces, if you will, for what linear algebra is about. It's about linear combinations. A little bit about how you're going to process this is going back to what we talked about in the syllabus. Your job, so this is all prior to class, your job is to read the associated section and watch the videos. For example, today we have two videos. We have this video, and then there's also the Grant Sanderson 3 Blue 1 Brown video. Those are excellent videos. They're all reasonably short. They're generally around 11 to 15 minutes, and he does a super job of presenting and building on our intuition. Sanderson tells us up front, his videos are not a course in linear algebra. He has strictly built them to help people understand what's happening, and that meshes exactly with what we are trying to accomplish in this course. And then, of course, as you watch through the videos, you're going to take notes. All the research shows that notes taken in your hand is the best way to learn. So pause the videos, rewind the videos. And that's why I'm saying, hey, it's fine. Play them at 1.5x and move through, but then pause. Write down things for yourself and make sure you're working through the examples. That's the other thing. So you're going to take notes, you're going to work through the examples, and then what you'll see is at the end of the video that I have created for each lesson, there will be participation questions. And these are questions which are overview, kind of high-level questions to make sure you get some of the basics down, and those questions will be discussed in class. We will be selecting people pseudo-randomly that will provide the answers to those questions. All right, so let's talk a little bit about vectors in Rn. Again, review for things you are familiar with. We have a vector v, for example, could be 2, 1. This is a vector which has two components, and those components are real numbers. This comes from the vector space, which we call R2. 2 is the number of components, and R represents the fact that we have real numbers. And we use this symbol, which means element of. So this vector is an element of R2. Another example, switch over here. So another example would be something like 3, 0, negative 1. So this vector is an element of R3. And the power of linear algebra is twofold. First of all, we can extend this idea. Everything that we talk about, all the definitions, all the concepts, everything extends as far as we want to go. If we want to talk about vectors in R100, no problem. R1000, no problem. Everything we're talking about applies to vectors of any finite dimension that we can come up with. And another thing, which we'll talk about in part, this is a couple of weeks down the road, but I just want to make you aware there are all of these ideas for linear algebra apply also to functions. And you can think for a minute about a function f1 of x being equal to 3 plus 2x minus x squared. And this is really just a linear combination of the set of 1x and x squared. So while I can have linear combinations of vectors, which means I multiply by scalars and sum them together, I can think about functions in exactly the same way. And this just begins to demonstrate to you the power of linear algebra and why this is such an important topic. We are not restricted to vectors with real numbers as components. There's all manner of things which we can define as vectors, and we'll talk more about this in a couple of weeks. Okay, a little bit more then about the information that Strang is providing for us. Most of this I'll let you read through. He talks about the fundamental components of the linear combination, which are scalar multiplication and vector addition. And then he goes on to have the conversation that, hey, I can end up building matrices by taking vectors which are length m and taking n of them and putting them together in what's called a matrix. And again, you've seen this kind of thing before, but it demonstrates the expandability, if you will, of the ideas that we're talking about. So here's this conversation about linear combinations, and then a little bit about the system AX equals B, which we'll talk about a little bit more. But first, let's talk about linear combinations, which are constant multiples times, and he provides constant multiples of vectors, scalar multiplication of vectors, and then summing those two things together. So again, just linear combinations. He provides an example. I've provided some vectors here, and what I want to do is I want to demonstrate for you a linear combination. So the linear combination of these two vectors would be some constant multiple of v1 added to some other constant multiple of v2. And what I'm going to do is I'm going to provide you with a video demonstration of what this looks like. So our tool for this course is MATLAB, and I have put the vectors that we're talking about right here inside of MATLAB. The green vector is of course green and the red vector is red. And it's difficult to see what's going on here, but in MATLAB, of course, we can drag this around and get a better view of what's happening. And now, and this is the kind of thing that I hope to provide for you to build your intuition and to give you kind of an expanded understanding of the stuff that Strang is talking about. You need to read the sections, typically only about 6 pages, but you're going to do that in conjunction with these videos that will help you to build, hopefully, better intuition and better understanding of what's happening. So we can develop our skills by practicing problems, although you'll see that a lot of the homework problems are also concept-based because that's our emphasis in this course. Right, so if we take a look at these, now we think about linear combinations, which is what linear algebra is all about. We're going to take each of these vectors and we're going to multiply them by randomly generated constants, and then we're going to sum those together, and it's going to show us a bunch of vectors in black. So each of these vectors in black is being built by a randomly selected C and D, and then summing those two things together. And you can see that it appears we have vectors all over the place. The reality is actually a little different than that. We don't have vectors all over the place. We have linear combinations of those two vectors, which means we are restricted to the plane in which those two vectors lie. We have created with what's called span. So I'm going to do what Strang does. I'm going to use the correct vocabulary without the definition. The definition will be coming. But this is the span of the green and the red vectors. The span is all possible linear combinations. So the span is this entire plane, because we can reach any point in this plane that contains the two vectors by using the right linear combination. And you'll notice that in order for us to fill up three-dimensional space, we would need a third vector, and we would need that third vector to not lie in this plane. And that's the conversation of independent vectors and dependent vectors, which we'll talk about in a minute. All right, so now we're going to move on to this concept of solving equations, which is something you're familiar with. Let me just write down the equations. So these are the equations that Streng has provided right here. And we can write them in this manner, which Streng refers to as the row way, where each row, and we'll see this when we build a matrix, each row represents an equation. So there's another way to think about this. We could also think about the fact that this grouping here is the constant c multiplied times the vector 2, 1. And this grouping here is the constant d multiplied times the vector 2, negative 1. And then, of course, that's equal to the right-hand side, which is another vector 8, 2. So what we have here is a different way to represent exactly the same situation. This is quite common when we're talking about mathematics. We're looking for ways to kind of improve or think differently about what we're doing. This is referred to by Streng as the column way. It's the column way of viewing a linear system of equations. And these vectors here are the coefficient vectors for the unknowns. Our unknowns are c and d, and the coefficient vectors are right here. And then finally, we have a different way of thinking about this, which is to make a matrix out of these vectors. We have a 2, 1 column vector and a 2, negative 1 column vector, multiplied by a vector of unknowns, c and d, is equal to the vector 8, 2. This is yet a third way of representing the same system of equations, and this is called the matrix way, because we have now taken these vectors, which are the coefficient vectors, and we've used them to create a coefficient matrix. So this is a coefficient matrix. My shorthand for matrix will be MATX. And what we're doing now is just looking at ways in which we could solve these problems. You'll see, and I'll try to point out as many of the typos, right? All textbooks have typos. Streng's textbook is no different. This is just the reality of it. What we have is we have a little bit of a typo here. Streng says that he's going to take 1/2 of equation 1, which he does, and then subtract that from equation 2. But when he does that, he actually writes down equation 1 again. So what I've done is that third green mark is I've written down equation 2. Please note the text over here is not designed as a replacement for the textbook, not at all. All I'm doing is showing you where in the text I'm referring when I'm talking about different things. You still need to have a hard copy of the textbook. So then he goes on to talk about what we just discussed, which is the column way and the row way and the matrix way of thinking about systems of equations. Let me go back for a second and just show you graphically what it is we're talking about. We have two vectors. We have the 2, 1 vector and the 2, negative 1 vector. And the question we're really asking is there a set of coefficients c and d such that I can build a linear combination of these two vectors that gives me 8, 2? Well, graphically, we're going to take a look at that. We'll draw one of the vectors, which is 2, 1, and that vector is right there. And then I have another vector. Let me change colors. I have this vector here, which is 2, negative 1. And then the vector that I'm trying to draw is all the way out here. This is 8, 2, right there. And when you read, when you watch the Sanderson video, and he'll talk a little bit about vector addition, and many of you are familiar with kind of the visualization of vector addition with the tip to tail, and that's the way we think about adding vectors. And so the question is there a way for us to multiply these vectors by constants and add them together to come up with the cyan vector, the 8, 2 vector? And the answer is, of course, yes, I can do that. I can take one copy of the red vector, and then I can add to that 3 copies of the yellow vector, and then we have created the cyan vector. So we know that 3 times 2, 1 plus 1, 2, negative 1 gives us what we wanted, which is the vector 8, 2. And these are C and D respectively. C is equal to 3 and D is equal to 1. It turns out that anytime we're solving a system of equations, this is the question we are asking ourselves. Is the vector on the right-hand side a linear combination of the columns or the coefficient vectors, the columns in the coefficient matrix? Can we actually build this solution? We'll talk more about that when we get to chapter 2. So there's this question about elimination actually not working. This process of what you learned. And I know there could be a question, why are we doing this? Why don't we just do what I did in high school and solve this problem using elimination or substitution? And the answer to that, of course, is quite straightforward. It's a matter of the fact that we could have an R, and oftentimes do, have an R1000 or an R1,000,000 set of equations, where we have a million different equations with a million different unknowns. And obviously we have no chance of solving that by hand. We need the power of linear algebra to help us solve that. And we'll be looking at those problems in the near future. But that's why we are doing this. But we also want to understand the questions that we're asking. So the question of, can elimination fail? This has to do with our picture again. So let me pull this up, right? And now we're looking at these two vectors that we have in R3, and of course any vector that's in this plane, we can come up with a linear combination of these two vectors that's going to represent it. When would we not be able to do that? When would we not be able to represent one of these black vectors? Well, that happens when we have linearly dependent vectors. And again, Strang just starts using the correct vocabulary, linearly independent and linearly dependent vectors. We will provide the formal definitions later, but what we're talking about is, we're talking about vectors like this. These two vectors are linearly dependent. And when we have only two vectors, the definition of linearly dependent comes simply from the fact that this is actually equal to negative 2 times v1. So when we have two vectors, if one of them is a scalar multiple of the other one, then we have two vectors that are linearly dependent. Let me show you an example in MATLAB. All right, so here are the two vectors, the red vector and the green vector that we have now. And of course we can spin this around and we can take a look at what these vectors appear to be. And we will build randomly generated linear combinations. But what you notice is the linear combinations all fall along the line that contains these two vectors. These two vectors are in a one-dimensional vector space. So they don't cover a plane. The linear combinations don't actually cover a two-dimensional object, they only cover a one-dimensional object. So any vector that's outside of that line, we can't represent as a linear combination of these two vectors. This is the situation where we could have elimination not working out for us. And that's the conversation he's having here, and the difference between linearly independent and linearly dependent vectors. Make sure you read through his example. It's different than the one that I've provided for you. Finally, we're talking about vectors in 3 dimensions, which you're familiar with just because that is the spatial dimension that we live in. And I just want to talk a little bit about standard basis vectors. So the standard basis vectors that you're accustomed to are I hat. By the way, Professor Strang does not put hats over his unit vectors. He just wants you to recognize them in context. I will try to put hats over all of the unit vectors just to differentiate them from vectors that are perhaps not unit vectors. So I hat you're familiar with. This is just 1, 0, 0. And then similarly, you know what j hat and k hat are. Those are the standard basis vectors for vectors that are in R3. I want to make a note to you that you can see these in other situations written as E1, E2, and E3. These are also used as a representation for the standard basis vectors in R3. And we can see the advantage of this immediately. If we're talking about vectors in R100 or R1000, it's very easy for us to reference what the standard basis vectors are. It doesn't take as long to run out of Latin letters and then we can't use this type of situation here any longer. And then finally, read this bit here about how do we know these linear combinations are in a plane when we're talking about two different vectors. That's an important part to idea to think about. Finally, what we have are the participation questions. So the participation questions for today are these three questions here. This is typical of what you will have. Three questions that you want to work through. They'll be reasonably straightforward as long as you've read through the text and you've worked or watched through the video. Let's see. So a little bit about just writing vectors down. A question from the Grant Sanderson video, the 3 blue 1 brown video, and then also a little bit of practice with how we represent systems of equations. That's it for the first lesson, and I look forward to seeing you in class. Thanks.